In section 1.3, we're going to talk about a few additional properties of functions, okay, being range, increasing and decreasing intervals, and minimums and maximums. Okay, and we have the three of these grouped together because for them we're mainly going to think graphically. These will be properties we find using the calculator. Okay, so here we go with first property we're going to take a look at is the range of a function. We're going to say the range is the set of all output values of a function, and when we say output we mean y values. Okay, so we plug the x values in, we get the outputs, the y values out, and the range is going to be all the resulting y values. Okay, again, thinking graphically, I have a function f of x on the screen, and as far as what's in my range, what's out of my range, I could say that y equals 2 is in my range. Okay, because for y equals 2, there's a part on the graph that corresponds with that. Okay, there's an x value that gives me that y value of 2. Same thing with y equals 5, okay, because I can find a part of the graph that corresponds with that 5. And if I looked at something like y equals negative 2, I'd say that that's out of my range, okay, because there's nowhere on that graph that corresponds with y equals negative 2. Okay, so that's kind of how we determine whether points or whether values are in or out. And then we can describe the range of the function in a similar way as we describe the domain. Okay, we've already looked at finding the domain of a function graphically. It looks like I have x values here running from negative 3, and then as the arrow continues, we'll say on up. So where are my domains, my x values, and we'd say from bracket negative 3 to infinity. The range, what we're going to do is just the same thing with the y values. This function's lowest point looks like it's at negative 1. Okay, and then it continues up for y values. So for this example, I'd say my range runs from negative 1 up through infinity. And with the range, generally what we're going to be looking at is kind of that greatest value or lowest value, okay, to use to describe it. The next way we can describe a function is by determining if its intervals are increasing, decreasing, or constant. We'll say a function's increasing on an interval if as x increases, meaning as x goes right, y also increases, so goes up. Okay, looking down at my function here, as x increases, that means as we trace the graph from left to right, okay, it looks like the first part of my graph is increasing, okay, because the y values are going up as we trace left to right. So I describe that using the x interval. We'd say it's increasing from negative infinity to x equals negative 1. Okay, so we describe the x's with the interval, and then the y's described basically by saying it's increasing or decreasing, going up or down. Okay, looks like this graph has another increasing interval. Looks like it's also increasing as we go left to right from 2 to infinity. So here it's a union positive 2, comma, infinity. Okay, notice with the increasing intervals, it'll be the same with decreasing and constant, but I'm not using brackets on these values just because it doesn't make a lot of sense to say that it increases exactly to a point when it turns at that point. So with increasing, decreasing, we'll always use our parentheses. Okay. We'll say a function's decreasing if as x increases, so again x goes right, y decreases, so goes down. Okay, it looks like as I trace here left to right from x equals 1 to x equals 2, our function's decreasing, the y values are going down. So I'd say decreasing from x equals 1 to 2. Okay, and then last thing we could have is the function could be constant on an interval. We won't see this happen much, but again, could happen. We'll say it's constant if as x increases, so goes up, y just stays the same. And we see that on our graph in the middle here, okay, as I go left to right from negative 1 to 1, okay, there's no change in the y values. It stays flat, kind of zero slope. I'd say my graph is constant from -1 to 1. So we have increasing, decreasing, and constant intervals. And the big thing to remember here is that we're talking x values to describe our intervals, not y values. And the last type of property we're going to talk about are local and absolute minimums and maximums. Okay, and describe mins and maxes, we're not going to worry about going into a technical algebraic calculus definition. We'll just kind of think graphically about it. When we say minimums and maximums, basically we're talking about the turning points in the graph where it goes from decreasing to increasing or increasing to decreasing. So starting on the far left, I'd say I have an absolute minimum. Minimum because it's a place where my graph bottoms out, and I'd say absolute minimum because it's the lowest y value my graph has. There's no part on the graph that gets below it. Okay, far right we have another minimum, but this one I'm going to call a local minimum. Again, minimum because the graph bottoms out and turns around, but local because it's a minimum for a portion of the graph. There's other parts of the graph that get below it. Okay, specifically our absolute minimum. In the middle, I'd say we have a local maximum. Okay, maximum because the graph tops out, but local because there's portions on the graph that go up above it. Okay, and with what we have pictured, I'd say there's no absolute maximum. Okay, because my graph's going to continue up in both directions, so there's never going to be a part where this graph actually peaks out and doesn't increase anymore. Okay, in general, there may be absolute mins or maxes. There may be local mins and maxes. There might be none in a specific graph. Okay, it's all going to depend on the equation we give you or the type of function we're looking at. All right, so let's take a look at finding all that different stuff for a given function. Problem 1 says find the range, local and absolute minimums and maximums, and intervals of increasing and decreasing of, okay, and we're given a function here. We'll take a look at a few examples, and we're going to take a graphical approach to this, okay, as in using the calculator. Without the calculator, this would be a probably half an hour long calculus problem. Okay, so we'll hit the graph button, and when you do that, you're really not going to know exactly what to expect until you see the picture. Okay, every function, every equation we give is going to work out a little bit differently. Okay, and along with the graphing calculator, I'm also going to want to make a sketch of what this is going to look like. Okay, just because I'm going to want to be able to write on this, draw on it, okay, label some parts, and it's going to help me find that different stuff. Okay, we're going to want to start off by finding the mins and maxes first because the range, increasing, decreasing, will be based on those. So to do that, we'll go second, calc. Okay, option 3 and 4 are minimums and maximums. We'll start off with a max over on the left side here. So we'll go option 4. And then to find that, it's a lot like finding zeros where I need a left bound, right bound, and a guess. We'll go to the left of that maximum, hit enter. We'll pass it on the right for right bound, hit enter, and then go guess. Okay, it looks like I have a maximum at negative 1.4 and negative 1.8. And we'll just do the same thing for the rest of our mins and maxes. So second calc, we have a minimum in the 0 next. Again, we'll make sure we're to the left of it, enter. Right of it, enter. Take a guess. So we have a minimum at negative 6 e to the negative 7. In other words, a decimal place, 6 zeros, then a 6. Basically, we'll just call something like that 0, and y equals negative 7. And then one more time for that final maximum on the right. Option 4 for maximum. Left bound. Right bound. Get up top for a guess. And our last maximums at 2.1 and 9.3. So we'll label those on our sketch. And then we can classify those minimums and maximums. Okay, starting on the left, looks like I have a local max. Okay, at negative 1.4, comma, negative 1.8. And we're going to give the x and y coordinates for that, so that's a point, not an interval. In the middle, we have a local min. At 0, negative 7. Then on the far right, we have an absolute max. Okay, absolute because there's no part of this graph that gives above this point. So we'd say absolute max at 2.1, comma, 9.3. Okay, next up, we'll talk about our range. Okay, as far as the y values this graph uses, it looks like it tops out at this maximum here, the 9.3, and then continues down from there, uninterrupted, no holes. Okay, so for my range, I'd say this graph runs from negative infinity up to the y value of that maximum 9.3. And as far as that 9.3 goes, I'm going to use a parenthesis here because it's not exact, it's rounded. Okay, it doesn't make sense to say equals exactly 9.3 just because we rounded things. Okay, then then the last thing we have to talk about are describing intervals of increasing and decreasing. Remember, that just means as I move from left to right on my graph, is the graph going up or coming down? Okay, the first part of my graph on the left looks like it's increasing from left to right, okay, because the graph is moving up. So the way we'll describe that then is using x intervals. All right, the y part is described by saying up or down. So I'd say that this graph is increasing from x equals negative infinity until we get to the x coordinate of this first maximum at negative 1.4. Okay, so we'll say inc as in increasing from negative infinity until we get to negative 1.4. Okay, then our graph goes down from left to right. We'll do decreasing in a second. And then in the middle it goes back up. So I'd say we're increasing once again. This time from x equals 0 to x equals 2.1. Again, I'm taking the x coordinates of these mins and maxes. So for increasing, we'll say union 0, comma, 2.1. Right, then we also want to describe the decreasing intervals. Okay, our graph starts by increasing, then it decreases from maximum to minimum here. Okay, because it's going down from left to right. And it's decreasing from the x value of that negative 1.4 till we get to the x equals 0. So we'd say decreasing on the interval negative 1.4, comma, 0. And then my graph finishes on the right by decreasing. It continues down on forever. And for those x values, we'd say from x equals 2.1 all the way on up to infinity. Okay, so there's all my kind of characteristics of the function we're talking about this section. Mins and maxes. Okay, so find those first, and we can describe them as local or absolute. Okay, find the range, that's going to be y values. And then our intervals of increasing and decreasing, those are going to be made up of the x intervals. Different ways things can work out. Okay, so again, we'll go straight to our calculator. Graphing this, so we have x squared divided by, and when we're dealing with rational functions like this, where there's denominators, numerators, if I want to put this in the calculator, I do need my denominator in parentheses. Okay, anytime there's two parts in a numerator or denominator, put those in parentheses. Okay, graph that, and again, we're not going to know really what to expect before we hit the graph button. Okay, something completely different looking here. Again, I'm going to make a sketch, so we're going to copy that down. Okay, we want to find the mins and maxes. Looks like there's a maximum here and a min here, so second calc. Okay, 4 for maximum. Go to the left, hit enter. We'll go right bound. Oops, I went too far to the wrong branch of my graph. We'll hit enter. And then for a guess, enter. And we get a negative 2.05 e to the negative 6, so basically 0. And same thing for the y coordinate. We'll just call that 0. Okay, and then for the minimum, option 3 for minimum, if I keep scrolling right, we'll get to that second branch of the graph. So left bound, right bound, guess. And we get a point at 1.9 repeating, so we'll call that 2, 4. So labeling those points, we had a maximum at 0, 0, and a minimum at 2, 4. Okay, we'll say those are both local because for my maximum there's an entire branch of the graph that gets above it. Same thing, whole branch below my minimum. So local max at 0, 0. And a local min at 2, 4. Okay, then the other thing I want to figure out for this graph is where this hole's happening. Okay, it looks like this graph has an asymptote at x equals 1. I can confirm that algebraically because as far as the domain of this function goes, we can't divide by 0. Okay, x minus 1 can't equal 0. That means x can't equal 1. Okay, that's how we know where this gap happens here. And graphically, that's what a gap like that's going to look like. Okay, anyways, next up, our range then. Range for this one's going to work out a little bit different because we have two separate parts of the graph. I have a first part on the upper portion that runs from 4 on up. But then there's a part on the lower piece of my graph that runs from 0 on down. Okay, combining those, we'd say our range is negative infinity to 0, union 4 to infinity. Okay, then last part, increasing and decreasing. Going left to right, my function starts off by increasing up to this first maximum. So we'd say increasing from negative infinity to x equals 0. Union, increasing again from 2 to infinity. And then it's decreasing from the first maximum down to the asymptote. So we'd say decreasing from 0 to 1. And then union, it decreases again from 1 to 2. And now I can't just say it decreases from 0 to 2 because at 1 it's not doing anything, the graph's undefined, so we do have to split that part up. Okay, so once again, there's our mins and maxes, range, and then increasing and decreasing intervals.